All right. Well, hello, Honors Algebra 2. This is our third lesson in this unit. So far, we've talked about how to collect data, the different ways that you can do that. We've talked about how you can display data, the different ways you can do that. Now we're going to focus on how you can describe data. So to do that, we're going to first start by talking about the two main types of data, which are categorical and quantitative. To start off with, categorical data, sometimes referred to as qualitative data, is data that consists of labels or non-numerical entries that can be separated into different categories. So that last part, categories, is why we typically call this categorical data. Now, categorical data can still have numbers. Uh, so when it says labels or non-numerical entries, those labels can actually be numerical values. So it's not as if categorical data is values that are not numbers. Quantitative data, though, has to be numbers. So for quantitative data, that's data that consists of numbers that represent counts or measurements. Typically, what you want to think of if you're trying to decide between quantitative and categorical. For quantitative, it should make sense to be able to find an average. If it makes sense to average the numbers together, that's going to tell you quantitative. If there's no numbers, or if it wouldn't make sense to average the numbers together, that is instead going to be where you would say categorical. All right, so to take a look at some examples of this, let's determine whether each of the data is quantitative or categorical. For quantitative, I'm just going to write Q, and if it's categorical, I'm just going to write C. All right, so for part A, 10 people rated a movie as poor, fair, good, or excellent. No numbers at all, not exactly like you can find an average for these, so this is pretty clearly categorical data. For part B, a chart gives the weights of 72 diamonds in a museum's gem collection. So they've got these different weights for our 72 diamonds. Would it make sense to find an average weight for the diamonds? And I would say it would. That's going to be quantitative data. All right, for part C, the list below shows the zip codes of the first 8 families to drive into Yosemite National Park on October the 6th. So we've got these numerical values. Well, it might be kind of an intuitive thing to want to say quantitative because that's kind of how we're trained. As we see numbers, we think quantitative. Here's the question. Would it make sense to find an average zip code? And the answer to that is no. It wouldn't make sense to find an average zip code. So actually, those zip codes describe where they're from. This is actually categorical data. So this is where you have to be careful where numerical values can actually be categorical. All right, for E, the list shows the times in seconds for each of the competitors in a 50-meter sprint. Would it make sense to find an average sprint time? And I would say so. That is quantitative. I'm not sure where example D went. We'll just skip whatever it was. And then for F, an employee at a theater records the gender of each person who purchases tickets at the box office. Would it make sense to find an average gender? And the answer there is no, so that is categorical data. Okay, there's a second kind of level that you can get when you're classifying data. So in addition to classifying categorical, and this says numerical, numerical being the quantitative data, there's actually two more kind of distinctions you can make, which is that quantitative data can be broken down into what's called discrete data and what's called continuous data. So the difference, discrete data is a set of values that consist of only certain numbers in an interval, usually whole numbers, whereas continuous is a set of values that consist of all numbers in an interval, which typically is where you're measuring. The way I always kind of think about these two to kind of keep them separate is discrete is like shoe sizes and continuous is like shoe lengths. So what I mean by that is when you go in to buy new shoes, like for me, for instance, I wear size 11 and a half. So when I go to the shoe store, I look at size 11 and a half, sometimes 12 if they run a little bit small, but I'm looking at kind of these whole values, like from an 11 to an 11 and a half to a 12. I don't go in and try to find shoes based off my shoe length. My foot length might be, 10.93 inches. But I'm not going to go into the shoe store and ask the person that works there for a shoe of size 10.93 inches. I'm going to ask them for a size 11 and a half. So the difference is shoe size can only be certain values, 9 and a half, 10, 10 and a half. So these half number values is what it goes up by. Whereas shoe length or foot length Could be kind of any number. I mean, you think about it, 10.93, maybe 11.12. There's kind of this more freedom with continuous than there is discrete. So let's maybe look at a few examples and hopefully it'll make a little bit more sense for you. So in this first example, and again, we're going to decide between discrete data and continuous. I'm just going to write D for discrete, and I'm going to write C for continuous. So don't think when I write C, I'm writing categorical. I'm now focused on discrete and continuous. So the players on Coach Mac's basketball team each attempted 20 free throws. So let's think about some possibilities. You could make 9 free throws. You could make 12 free throws. You could make 15 free throws if you're good. Could you make 14.2 free throws? And the answer is no. You can only make a whole number of free throws. That means that this is going to be discrete data. All right, for part B, on June 1st, a student recorded the day's high temperature in several cities around her state. So maybe 72 degrees, maybe 75 degrees. If you got a little more specific, you could probably say 74.1 degrees or 71.2 degrees. We're not really limited by these whole number of values. That's going to make this continuous data. Again, this is where this idea of measuring becomes kind of important. So for C, the fire department mandates that all firefighters must weigh between 150 and 250 pounds. Okay? Well, that means that they could weigh 155, they could weigh 168, they could weigh 227.41. They could weigh anything as long as it's between 150 and 250 pounds. That's going to make this continuous data. Okay, so that's one thing that we need to make sure we understand is describing continuous and discrete. Now let's focus more on describing the data displays themselves. And we're going to do that by talking about this acronym. And the acronym that we use oftentimes to help us remember is SOX, not the things that you're wearing on your feet right now, but just an acronym to help us remember how to describe each part of the data. The first S stands for the shape of our distribution. So I've got some examples of the different shapes there for you. The first being symmetric, being that if you cut it in half, it would look the same. Unimodal, meaning that it's got kind of the one peak here at the very middle. And then bell-shaped, again, I kind of drew that over the top of it for you to look at. The next is skewed right. So you can see with skewed right that most of your data is actually to the left. So the skewed right actually means that kind of the tail of the data is to the right of it. The next is non-symmetric and bimodal. Non-symmetric meaning that if I drew a line to try to cut it in half, they don't look exactly the same on either side. But bimodal means that it's got a couple of different peaks. That it's got kind of one peak right here and a second peak right here. So for 2, that's why we're calling it bimodal. Uniform just means that the data kind of looks all the same, kind of uniformity of the data. Skewed left is the opposite of skewed right. So skewed left, you've got your tail to the left and a majority of your data actually to the right. And then symmetric bimodal kind of being the same as what was up here. The one difference being that when you draw a line down the middle, it now does look the same on either side. So the O in SOX stands for outliers or unusual points or unusual features. Sometimes this gets included with the spread, and so some people just say SCS. We'll go ahead and call it SOX, just to make it easier. Now, a couple things to talk about with outliers. The first is the idea of what's called a gap, which is areas of the distribution where there are no observations. So when you look for a gap, that means that you've got kind of your data on the left, you've got your data on the right, but there's this kind of gap in between, which are important because that's how you can recognize outliers. So outliers are any extreme values that differ greatly from the other observations. So not only do you have a gap, but that means that there's kind of this one single point that's further away from all the others. That's where you get into the idea of an outlier. The C stands for center. This is numerical descriptions of distributions begin with the measure of its center. We kind of have 2 options for that. The first is the mean, which is an average. This is a sum of all the numbers in your data set divided by the number of the other values. I've written it like this. This sigma, which is a Greek letter, means the sum of, and then x just means all the observations. So the sum of all your data values divided by n, and n represents the number of values in the data set. So again, sigma here represents the sum, so you're adding them all together. X just means all of your observations, and n means the number of your observations. So there's kind of what each of those means. The median we've already talked about as well. That's just the middle number of your data set. All right, the last S stands for spread. And that's really kind of the key to stats. If everything looked the same and it was uniform, there'd really be no reason for spread, and there's really no reason to study it. So the variability is kind of where we get into more of the fun stuff. So a few different ways you can describe it. The first is probably the most basic, which is the range. Take max minus min. The second way is quartiles. That was the idea of what we had in the previous lesson, which was the interquartile range that we used on the box plot. Those are the values that, if you recall, divide the data into 4 equal parts. The next two are probably new. Variance is a measure of how much a typical value in a data set differs from each of the other values. The formula for variance of x is that you take the standard deviation s sub x squared. We probably won't use variance so much this unit as we will standard deviation. So this is the more important one to know. So first off, just understand that the standard deviation always goes along with the mean. So standard deviation is a measure of how much a typical value in a data set differs from the mean. So in other words, you're talking about what is the average distance from our mean. The formula for that is kind of complicated. I've got that here for you. It's the square root of the sum of all of your values x sub I minus your mean, which we write as x bar squared over n minus 1. Well, there is the formula. This is going to be something that we're going to use your graphing calculator to find. So don't think that you're going to be doing this by hand. If you want to see it by hand, I might have time to make another video for that if you ask me for it. But otherwise, we'll probably just use graphing calculator for it. So let's talk about how to find some of these values. Especially, let's talk about how to find outliers, and then we'll do some practice with stocks. So McDonald's fish and chicken sandwiches. I've got the data here on the amount of fat in grams of the 9 different McDonald's fish and chicken sandwiches. We're going to calculate the median and interquartile range. So you've got everything from the fish fillet up to your southern style crispy chicken sandwich. And fat in grams, I'm going to do this using graphing calculator just to remind you of how to do that. So the first thing, if you want to use your graphing calculator, is you'll go to stat. You'll choose that first option, number 1, for edit. And then you'll put all of this data into list 1, which, if you notice, I've already done here for us. So 19, 16, 22, 33, 27, 9, 20, 14, and 19. So in order to get the values then that I want, I'm going to go back to stat, over to calc, 1var stats with list 1, and hit calculate. And that's going to give me the values I want. If I scroll down, it's going to tell me that my median is 19. So that would be the first thing that it wanted. And then for interquartile range, we're going to have to take Q3 minus Q1, which Q3 it tells us was 24.5, Q1 was 15, and if I subtract, I get 9.5. So pretty easy, especially if, like I showed you, if you use your graphing calculator, it makes it a whole lot easier. Let's talk about how you can actually find outliers. So to find the outlier numerically, a data value that is much greater than or less than the other data or values in the data set is what's called an outlier. To find that, any observation that comes outside of these bounds is an outlier. So the bounds that we're going to find, kind of our boundaries, if you will. For the lower bound, we're going to take Q1 minus 1.5 multiplied by your interquartile range, hence the 1.5 times IQR rule. For the upper, we're going to take Q3 plus 1.5 multiplied by your interquartile range. So I've switched it up a little bit. I've got the data for the amount of fat in grams for McDonald's beef sandwiches this time. Let's figure out if there's any outliers in our distributions. We've got everything from the lowest of the hamburger, so not surprisingly, the most simple is the lowest in fat, all the way up to the fattiest one, which is the double quarter pounder with cheese, which again, can't say I'm all that surprised by that. So let's do this. Let's make it a little bit easier on ourselves to find those values. Let's go ahead and put them into our calculator and use that to help us find our median as well as all of our other values for the quartiles. So in edit, you're going to notice that I've already got mine into list 2. If you just want to type them over the top of the ones you had in list 1, that's fine. I just wanted to go a little bit quicker through this video, so that's why I've got them in list 2. Which means for me, since I've got them in list 2, when I go back to stat and over to Calc, when I choose this one var stats option, I need to make sure that instead of list 1 that this says list 2. To change it to list 2, all I have to do is hit second, and then above the 2 button, you'll notice that it says L2. So when I hit second 2, that pulls up list 2. And then I can go ahead and hit calculate the same as I would otherwise. If yours doesn't have the menu, then after one var stats, you just have to type in list 2. So you would just hit second L2. So on your home screen, it'll say one var stats L2. And then when you press enter, you should get the same values that I'm getting. So the ones that are most important is really focused on Q1 and Q3. So it tells us that Q1 was 21 and that Q3 was 29. So in order to use these formulas, we've got Q1, we've got Q3, we just need to find our IQR. So IQR, remember, you're just going to subtract those numbers. 29 minus 21 is 8. So now we can focus on our lower and upper bounds. For the lower bound, we're going to take 21 minus 1.5 multiplied by 8. So that would be, let's see, 21 minus 12 is 9. So that'll be the lowest number that's acceptable. For the upper, we're going to take our quartile 3, which is 29, plus 1.5 multiplied by 8. So that's going to now become 29 plus 12, which is 41. So we can't have anything lower than 9, and we can't have anything more than 41. So looking at our values, most of them fit between 9 and 41. Even though hamburgers had 9, that's okay. We're good to go with that. But there is one that's higher than 41. And that was our quarter pounder with cheese, double quarter pounder with cheese, actually. So are there any outliers? The answer there is yes. 43 is an outlier. So if you don't have a graph to go off of, this is kind of what you have to do in order to find outliers. Okay, let's do one last example here of actually describing using SOX, the different data displays that I've got here for us. Let's start with A. Our shape for this one, we'll compare it to the ones that we had on the previous page. It looks like it's got a single mode, so you could say unimodal. It's also symmetric, and so we'll probably just say symmetric as our description of it. You could also say unimodal if you wanted to. Let's just go across. So the shape for the second one, it's got its tail going to the right. So what that means is that this is a right skewed graph or skewed right. And then for the last one here, even though you've got this outlier, I would say the graph is pretty much symmetric otherwise. So I'm going to go ahead and call it symmetric, and I know it's not perfect because if you draw a line down the middle, you're going to have this value that's kind of off, but I think that's about as close to symmetric as you can get. I would say both A and B pretty clearly you don't have any outliers. I would say C pretty clearly you do have an outlier. So we're going to say that there's an outlier at 15. Okay. For the next one, for center, it looks like this one on part A is centered right around 4. For part B, probably somewhere around either 1 or maybe between 1 and 2. I'm just going to put 1 to 2 there. And then for C, pretty clearly, the center there is at 5. For spread, let's just use the range. I think that'll be easiest to talk about. This one goes from 1 up to 7. 7 minus 1 tells us the range is 6. Here we've got 1 up to 8. So 8 minus 1 is 7. So the second one's a little bit more spread out. And then this last one here, you take 15 minus, I guess the lowest number would be a 1. So 15 minus 1 is 14. So a lot more spread out. If you get rid of the outlier, think about what would happen. Now you've got 10 minus 1 is 9. Now you've got something a little bit closer to the other two, which will be something we'll actually talk about in this next section of the notes. So we'll spend a little bit more time talking about those measures of center, measures of spreads, talking about mean and standard deviation. That'll be what we'll talk about in 11.4. But that's all I've got for us today. Have a good rest of your day, guys, and I will talk to you next time.